Oops. Okay, let's keep it like that. Okay, so welcome to lecture 27, which is the second to last lecture in convex analysis for this term. Okay, so the title of today's lecture is Preconditioned Proximal Point Methods. Okay, so and let's just recall what the proximal point method is. I think we just talked about it in the last lecture, but anyway, so we call that this is the resolvent. It's denoted in that lecture by JA, and it's just 1 plus A to the minus 1, and as long as A is monotone or maximal monotone, this is always guaranteed to exist, be defined everywhere, and single valued. So because of this, we can always just do a fixed point iteration for the resolvent operator. AN is mapped by the resolvent JA to xn plus 1. This gives us a sequence, and we've proved in the last lecture that the sequence is converging, converges to a solution of this monotone inclusion as long as one of these solutions exists. Of course, we could also introduce step sizes here, so because this inclusion here simply does not change at all if we, and of course you can do that as well. Okay, so but applying the resolvent is also solving a monotone inclusion, but with the operator identity plus gamma A instead of A, which is probably not simpler than solving the original inclusion in somehow. Okay, but preconditioning is something which can really help and may turn this into a very practical and broadly applicable algorithm. And so let's start illustrating this by in the context of Fenchel-Rockefeller duality. So Fenchel-Rockefeller, and we've seen this in section 15 and 16. So there we had an optimization problem, not a monotone inclusion, of the form minimize f of x plus g of kx, and I think maybe it was a back then, but now we use k because a is our monotone operator here, over x, and we have that these f is a convex map from Rn to the extended reals convex LSC, and of course proper. K is then mapping from Rn to Rm, so a linear map, so a matrix, and G is then on Rm mapping to numbers as well, convex and LSC. And let's assume that everything is nice enough such that we can fully apply Fenchel-Rockefeller duality. So this is the following optimality system, which there we had different formulations, but one of them was minus k transpose of y lies in the subgradient of f at x, and k of x lies in the subgradient of the adjoint, the conjugate of g at y. So, and in the context of Fenchel-Rockefeller, you can say that x is a solution of this minimization problem if and only if there exists a y such that these inclusions are fulfilled, and this if and only if the y solves the dual maximization problem, or x and y are a simultaneous solution of the saddle point problem. Okay, so what we're now going to do is we reformulate this optimality system 2 times. First, we just move everything to the right hand side and form inclusions 0 is contained in k transpose y plus subgradient of f at x, and here 0 is in minus kx plus subgradient of g star at y. Okay, nothing bad happened, we just moved this to the other side. This is usual Minkowski addition, and so this is exactly the same. And now we formulate this as a block operator. So if you have here x and y as a tuple in Rm times Rn, and then of course we could also stack the zeros to one vector in also Rn times Rm. And so what is now the operator in front of here? In the first inclusion, the x goes into the subgradient and the y goes into k transpose. And here down here the k goes into minus k, the x goes into minus k, and the y goes into the subgradient of g star. That's now the block operator form of this optimality system. Okay, and so let's call this guy here so script a in the following, and this variable here will be called u. So this a is a multi-valued operator from Rm plus n to Rm plus n, and the u is of course then contained in Rm plus n. Okay, now this A, it's a block operator, and it's multi-valued monotone, multi-valued from Rm plus n to Rm plus n. Is it also monotone? Can we see that? And yes, we can, because we can decompose it additively into two sub-operators. One is that guy here, and the other is this here, k transpose minus k. So this here is monotone, even maximally monotone, since these operators on the diagonal are monotone, and then it's just so if you just concatenate operator on the diagonal monotone ones, then you get a monotone one. That's, and also the same holds true for maximum monotone ones. So since monotone, since subgradients are monotone. And what about this one here? That's also monotone because it's skew symmetric. So monotone as well. Skew symmetric operators are always monotone. So if B transpose is minus B, then we always have, and so skew symmetric and linear. So for linear operators, to check monotonicity, it's enough to just check this here, that these guys here are non-negative. And in case this is skew symmetric, this is the same as U B transpose U by the definition of the transpose, but this is minus U B U by skew symmetry, and this is of course by symmetry of the inner product. It's the same as minus BU times U, and from this follows that BU times U is equal 0, because it equals it's negative, and 0 is largely equal 0. So skew symmetric operators are always monotone, and linear operators are continuous, so they are also maximally monotone. So now one minor problem is that although both operators are maximally monotone, it's not in general true that the sum of them is still maximally monotone. So monotonicity is preserved by sums, maximality not always, but not go into detail about this, and always assume in the following that this full A here is maximally monotone. Okay. Just for simplicity. Okay, so now we formulated this minimization problem here as a monotone block inclusion in the primal dual space. So this is the primal space is here, this comes from the dual space, and this is now the full primal dual optimality system formulated as one monotone inclusion. So, but now the problem persists, calculating the resolvent of this operator here, so this block operator is the same as solving that inclusion, and this is just the same as now it's the same, but solving the inclusion is the same as this. But if you now have a close look, what is the resolvent, or how does the equation for the resolvent look like, or the inclusion, it's still difficult and it's not clear what to do about. But here comes the big if. So now the big point is here that there's a simple way of doing preconditioning to this inequality, to do this to this inclusion here. And recall, did we talk about this general idea of preconditioning? Yes, we did in the end of the previous lecture, I guess. Right, we did already. So the idea of preconditioning was, so it's also a recall from the last lecture. So if you have this inclusion here, let's call it AU, this is fulfilled if and only if you have this here for M symmetric positive definite. And yeah, that was that. And then one can see that, so this was one point to recall, that we can just left multiply this inclusion by some symmetric positive definite operator, and then we preserve the solutions. And now comes the point that this resolvent here of that guy, although this is generally not monotone, but anyway, this operator here, we could show that this is exactly the same as that. And you see, to apply this resolvent, even though this m to the minus 1a is in general not monotone, this here, to apply this, you need to invert m plus a. So you don't need to invert m to invert this here, you only need to invert m plus a. And now that gives us something, so we can now try to cleverly choose an m which we add to the a, which makes this m plus a invertible, simply. Okay, and what we can do, so let's have another look. This a is this guy here. So, and if we recall what we know about 2x2 matrices, inverted 2x2 matrix is totally, or inverting any matrix is simple, or solving a system with the matrix is simple if the system is triangular. And now here we could try to aim for block triangular, because we can invert the diagonal entries, not the diagonal entries, but we can invert identity plus, let's assume that we can invert identity plus subgradient of f. This would be done by the prox, and identity plus subgradient of g star would be the prox of g star. So we try to cancel out this guy here in the off diagonal by a suitable m. So what we would need then here in the upper right would be a minus k transpose. So if we have this here, then m plus a would have a 0 in the upper right corner. That's good. But now we constrained our m to symmetric positively finite, which means we need minus k down here to have symmetry. So and what can we put on the diagonal? Well, it should be symmetric things. That's one thing. It should be such that the full operator is symmetric positively finite, so not only symmetric but also positively finite. That's not clear, I'd say. We're going to check this later. But also, we would need that this operator here plus this has a simple inverse. Yeah, well, and this is not the case so often, but so what we're going to see is 1 over tau times identity makes sense. And 1 over sigma times identity for some tau sigma. Let's just constrain them to be positive here, because so of course 0 does not work. Negative would be difficult to evaluate to invert the identity, the sum here, but we'll see. Okay, and now this is our choice, and now comes the lemma, which shows that this works perfectly. The lemma goes like this. If we have our setting here, so K is an m by n matrix, F is from Rn to the extended reals, and G from Rm to the extended reals, both proper, convex, and that is C. And we define a vector u plus, which has the components x plus and y plus, which should be just one preconditioned proximal point step by m plus a to the minus 1 m applied to x, y, with this m and this a here. This is the m, this is the a. And then we see that this x plus is actually the prox of tau times f of x minus tau k transpose y, and the y plus is then the prox of sigma g star of y plus sigma k times 2x plus minus x. Oops, I'm off screen, sorry. So down here, x plus is the prox of tau f of applied to x minus tau k transpose y, and x plus is the prox of sigma times g star applied to y plus sigma k applied to 2x plus minus x. Okay, so and this is now good, because we can just, if we are given x and y, so which then will be xn and yn, we can calculate one step of the preconditioned proximal point method explicitly by just using applying k transpose and k, using the proxies of f and the prox of g star, and that's it. So we can do it like this. We first calculate the update for x, and then we use the update for x to calculate the update of y. But it works, so it's nothing implicit anymore. So although the x plus appears on the right hand side here, we can just compute it without using y plus. Okay, let's prove this. It's a straightforward calculation. We just write down this inclusion here. So this guy here is the same as, so we just write that out. Now we just write it first, we bring these to the left hand side. X plus y plus contains now x and y, and we just spell that out. So here we have, oops, I have to keep it down. Here we have m plus a, and we just calculate it and put it here. So those m gives 1 over tau times identity plus subgradient of f. In the upper right corner we have minus k transpose plus k transpose, which gives us 0. In the lower right corner we have minus k gives us minus 2k. In the lower right corner we have 1 over sigma identity plus subgradient of g star. Okay, and then this is applied to x plus y plus, and contains oh, there was something missing. It contains m times xy. So here we have again m, it's 1 over tau identity minus k transpose minus k 1 over sigma identity applied to x y. Okay, now we treat the two inclusions one after the other. So the first inclusion is just we multiplied inclusion multiplied by tau, which is all positive, so this is, doesn't destroy anything. This is identity plus tau times f, this applied to x plus, and this contains, this by tau is x minus tau times k transpose y. Okay, and here we recognize that the inverse of identity plus tau times subgradient of f is exactly the prox. So you can solve this by applying the prox of tau f of x minus tau k transpose y. And this is already our first update here. Okay, good. And now for the second, we do basically the same things. The second inclusion multiplied by sigma gives us, so now we have to be a bit careful, it gives us a minus sigma to k x plus identity plus sigma subgradient of g star of y plus contains, this also by sigma, minus sigma kx plus y. Okay, what we do now is we bring this to the right hand side, reorder the right hand side, and solve by the prox. This is the case if and only if y plus is equal to the prox of sigma g star applied to, then we have this y. This goes over the plus, so we use a plus here plus sigma. Both have a sigma here, both have a k, and then we have 2x plus minus x. And that's exactly our second update, and that was the full proof actually. Okay, so that's a good thing. So it tells us that we can use this m, this preconditioner which we defined up here, to obtain tractable iteration. So doing this, applying this, the resolvent of m to the minus 1a is actually possible by applying the prox operators individually of f and g star. So no need to apply the prox operator of f plus g or something like this. We need the prox of f and of g star. And we need to apply the matrices f, g and g transpose. Okay, that's actually great. Because as we'll see, this is good in, this is the case, or the situations like this occur all over the place. So, but there's one thing left. So we could not conclude yet that that the preconditioned proximal point method converges, because what is missing is positive definities. So we need, so we check M for SPDness. So is M SPD or not? Okay, so what we need to check is inner product like this, U times MU. Okay, because if this is positive difference, this is always positive, then this is actually defines a new inner product. So this then defines an inner product which we call it like this. and you want to check if this is always positive. Okay, so let's decode that. It's then here xy times 1 over tau identity. Then we had minus k transpose minus k 1 over sigma identity times xy. Okay, so let's just write that out. So I'm always on the slow side here. Maybe I first expand the right side. This is here then 1 minus tau times x minus k transpose y. And here we have minus kx plus 1 over sigma y. And now the inner product gives us this times this is 1 over tau times norm x squared. This times this is minus x k transpose y. This times this is minus y kx. And then we get plus 1 over sigma y squared. Okay, we see that these both here combine to minus 2x k transpose y, or let's write it differently. That is of course true, but we could also say minus 2 kx with y. And the point is here that this is by Cauchy-Schwarz in the other direction, larger or equal to minus 2 norm k, norm x, norm y. So then this here is larger or equal to 1 over tau norm x squared minus 2 norm k, norm x, norm y plus 1 over sigma norm y squared. So now this here is a quadratic polynomial in two variables, the variables x and norm x and norm y. And so when are quadratic polynomials positive? So this is now when, question is now when is ax squared minus 2bxy plus cy squared positive for all x and y. And in this case, that's very simple. This is if and only if this a is positive and the discriminant ac minus b squared is positive. That is not too hard to see that this is the case. B squared. So we see that this here is positive if and only if so our a is 1 over tau, so we need tau positive, and ac minus b squared, so a and c is 1 over sigma tau minus the k is the b is just the k, norm k squared, also positive, and this here is equivalent to say that sigma tau is bounded by norm k to the minus 2 and also positive. Is it? Did I mess that up again? No, that's how it is. Okay, yeah, true. Okay. So this is the condition, and this is a simple condition, and we need to know the norm of k. That's it. And if we know the norm of k, we have still some freedom in choosing sigma and tau as we like. Okay, so now we have already proven that some algorithm does always converge to a solution of an optimization problem in Fenchel-Rockefeller form. So in this we collect as theorem. So what we have proven is theorem 27.2. Under our conditions, k is again m by n matrix f from Rn to R, and G from Rm to R extended, proper, both of them proper convex lower semi-continuous, x0 in Rn and arbitrary, y0 in Rm arbitrary. And then you can say if the saddle problem minimize over x, maximize over y, f of x plus kxy minus g star of y has a solution. And then the iteration xn plus 1 is equal to the prox of tau f xn minus tau k transpose yn, and yn plus 1 equals to the prox of sigma g star yn plus sigma k 2xn plus 1 minus xn. Then this converges to a solution, if sigma tau is smaller than k norm k to the minus 2. And then what else is true is that the xn converges to a solution of the primal problem, and the yn converges to a solution of the dual problem, as long as all these things exist. So they exist because by solvability of the saddle point problem. And we've just proven that. There's nothing left to do. It's already everything it's everything available. So we know that this m is now, we know that this iteration is indeed a preconditioned proximal point method. It's a proximal point method in the space where the inner product on our m plus our m plus n is given by the matrix m. That's positively finite, so everything is nice. And now we prove the general result on convergence of proximal point methods. So nice, and this now method is known as Chambol-Popp method. Also known or primal dual hybrid gradient method. It's basically from primal dual hybrid gradient method. Gradient, I don't know, so because this here looks like gradient descent and ascent step, but it's a little shaky. Chambol-Popp are two guys who came up with the method in 2010 in a similar format. Already has been prevalent in other papers of primal dual method, but I think this is now the common name. It's 2011, so it's only 10 years old. And as far as I'm aware, it's the first general method which is really able to solve all these kinds of problems. And in the French Rockefeller format, you only need to be able to apply the prox of f, the prox of g star, and apply k and k transpose. No matrix solves are involved, even no gradient computations, if that matters, and no smoothness is used actually. Right? You don't need any smoothness for f or g, nothing at all. Only the kind of proximability that you are able to apply the prox. Okay. Good. So this was probably worth noting that these are the only things which you need to be able to do, and probably I illustrate. Yeah, maybe I do that right now. So this is not in the handout, not in the lecture notes, but maybe I just do it right now and show you examples where this works. For example, this works. So let's do some examples, even though they are not. So, for example, a lot of inverse problems. We talked about inverse problems because inverse problems for linear operators. Inverse problems. So let's call this one inverse problem. In this case, we want to solve kx equals y delta, something like this. So this is a linear forward operator, and we have a perturbed right-hand side y delta, and we want to find an approximate solution x such that kx is very close to the original y, which we haven't seen. We've talked about variational regularization already. Variational regularization, which was of the form minimize two terms, the discrepancy terms, so a distance here which penalizes that we don't have data match. Let's say it's f. Let's don't call it f, because let's call it capital F for now. Of x minus y delta, plus then let's call it alpha, and then regularizer of x. So when this should be small if kx minus y delta is not too large, and this would be small if x is a reasonable solution. So this is the discrepancy term here, and this is the regularizer. This is the similarity measure, and this is the regularizer. And of course, this falls under the general framework. So maybe even more concrete. We could use, for example, we want to minimize, let's say here, let's say kx minus y delta, for example, in the 1 norm, to say to take something which is non-differentiable, and here alpha may be also the 1 norm, so why not? So here you penalize, or you regularize by the 1 norm of x. We've seen that this has sparsity-inducing properties in the lecture and in the exercises, and you may even measure the discrepancy also in the 1 norm, for example. So it's a kind of, looks like a nasty non-differentiable problem. Of course, you can try a subgradient descent on that one. But subgradient descent, we know that is painfully slow, and step sizes are a pain, and so it's not very nice. So gradient steps are out of question because we don't have any differentiability, so there's no way to make a guaranteed descent step by gradients. Even subgradients are not helpful. But we can now apply the Chambol-Pock method here. This works always. So this is our f of x, and this here is our g of kx. So what g of y would then be, let's not call it y, let's call it g of, let's call it c. No, let's call it just, what to use, let's call it g of p. G of p would then be just p minus y delta. Okay, now to apply the Chambol-Pock method, we would need the subgradient, or you need the prox of tau f of x, which is the prox of tau times alpha times 1 norm. And we know that this is the soft thresholding of tau times alpha of x, which was the min of absolute value of x minus tau alpha 0 times the sine of x. This function here, and this is tau alpha. Oops, so this function there. That is simple. And now what about the prox of g, the prox of g star? So we need to calculate g star. So g star of y would then be the supremum over y times p minus 1 norm of p minus y delta. So you see that we have calculus rules for this. So what do we? I know what the conjugate of the 1 norm is. It's the infinity norm, but I always forget how to do this. So I always have to do it by hand. But it's not that hard. So it's a supremum over p actually. So we just substitute. We say that q is p minus y delta, and then this is the supremum over q. And p is replaced by q plus, so this is y, and then it's here q plus y delta minus 1 norm of q, 1 norm of q, right? So and this is then, this goes out, y minus y delta plus the supremum of y times q minus 1 norm of q, and this is exactly the infinity norm of y. So we need the prox of this guy here, and so I'm too lazy to calculate, but it's the prox of the infinity norm, which is the projection onto the infinity norm ball, which is very simple, plus a linear shift in one of the directions. I always forget. So the prox of g star is also simple as well. It's a shift, so I think it's plus y delta. So plus sigma y delta, and then project back onto the infinity norm ball. Everything is pretty straightforward to calculate, and if you guarantee by some means that this has a solution, and this I guess in finite dimension always has a solution because it's proper convex, lower semi-continuous and coercive enough. Yeah, I guess so. Yes, it is. So you always have a solution. You don't have unique solutions, but Chambol-Pock is guaranteed to converge to a solution. And the only thing which I was too lazy to do here is to calculate the prox of g star. But it's not a big deal. You can do that in 5 minutes, I guess. Okay, so and you could choose all functionals here you like as long as you are able to calculate the prox. So you can can use a lot of regularizers here as long as you're able to calculate the prox operator of this, and here you only need to calculate the prox of the similarity measure after taking the operator k. So the operator k kind of can be decoupled from the functional here which we used for measuring the discrepancy. Okay, nice. I think it's time for a short break, and I will be back in 2 minutes. It's still old jokes, but I need 2 minutes break, and you maybe as well. So it's a short break, and I'll be back in 2 minutes. Okay, so that was that. So we finally were able to recover this general purpose jackknife method, which always kind of, or Swiss Army knife, which always kind of works. Okay, so now another point is, so the edge case. Sigma times tau equal to norm k. This is excluded. But for a kind of strange reason, it is excluded because at that the preconditioner fails to be positive definite and becomes in general positive semi-definite. So this was the only thing we needed this here to make this to have here a sharp inequality. If we only have equality up here, then we only have inequality here, and may have equality, and we're gonna have equality at one point. So this is the only thing. So it's really it seems like not a big deal, and in fact it's not. So we can include in the edge case, and this opens the possibility for quite a number of more general algorithms. So for example, if k is the identity, then sigma equals tau equals 1 does not work in our theorem. So, but let's still have a look. We're gonna have a look at this situation in a more general case. So more general than this Fenchie-Rockefeller duality is the case of split monotone inclusions. Split monotone inclusions, and these are inclusions of the type 0 is contained in a plus b of x, and let's say a and b, and maybe a plus b as well. That's not so important for our discussions here, are maximally monotone. And we assume that we can the results of A and B are simple to apply. So in the sense, as before, that so kind of applying JA to some vector x is a simple task which takes about linear time or something like that. So time linear in the dimension maybe. Okay, now let's see how we can tackle this. We do something which is actually very similar to what we've done with Chambol-Pock. So first, of course, we observe that this is the same as that. 0 is in ax plus bx. But now comes, this is the case, if there exists a y such that y is in bx and 0 is in ax plus y. So this is just a reformulation of this set-valued inclusion. So these are both sets. So when do we have 0 in the sum of the sets? Yeah, if there's one element here which adds to another element of there to 0. So this is kind of necessarily it's an existence result. There exists a y in this set such that 0 is in y plus that set. Okay. So but this here now is equivalent to 0 is in and now I do, so of course it's equivalent to say that this is in minus y plus bx, but this will not be helpful. So this is true but not helpful. What is also true is we can bring b to the other side by just using the inverse, which sounds like a big deal now because inverting b is what we're trying to do here. Actually not, actually we try to invert a plus b, but okay. So it's x in b to the minus 1 y, which is the same as say 0 is in minus x plus b to the minus 1y. So now we have this here is equivalent to there exists a y such that 0 is in ax plus y and 0 is in minus x plus b to the minus 1y. And this again we can reformulate as a block inclusion. The block 0 is contained in, and then here x, y, and then you have a identity minus identity, the interior of b to the minus 1. Okay, so now what we did is we reformulated this split inclusion. So split means we split up the right hand side, the monotone operator, into two parts additively. So we write the right hand side as a plus b, and we ended up with this inclusion here of a block inclusion of just one operator, and this here again is of the form a 0 0 b to the minus 1 plus a skew symmetric linear operator. This is monotone, sum is monotone, that's a monotone operator again, and we call that a. And then again, so if these a and b, I forgot to say that I'll go from x to x, then we define script x as x times x, and we see that a, which is now from this script x multivalued to script x, is monotone again. But probably let's just keep it like this. I think maximality is again not true, but I haven't thought about this. But it may be true, but I don't know. It's actually not so important for our discussion. So this is seems like a little bit more general. It can also be seen as a special case of what we've done before, but anyway, it's a different formulation now in the world of monotone operators. And split monotone inclusions are also a big thing. So for example, you can formulate all these Fenton-Rockefeller stuff also as a problem of split monotone inclusions. Okay, now the nice thing is we're in the same setting as before. We formulated this as a one inclusion in a product space. We decoupled A and B. One thing which may seem like a problem is that we have b to the minus 1 here. We will take care of that later on. But this just resembles that we got subgradient of g to the minus 1 in the previous derivation of the Chambol-Pock method. Because subgradient of g of the conjugate, sorry, subgradient of g conjugate, because this is actually the inverse of the subgradient of g, right? So we also had an inverse here in that place, and we derived the Chambol-Pock method. Okay, so now we do the same thing. We do a preconditioning of this inclusion with some m, script m, which is again of the form if we add it to A, we want to that one of the off-diagonal entries cancel. So here we put a minus I here, then we have a minus I there, and here again we put something like 1 over tau identity, 1 over sigma identity, just to make everything work out. And here it's simple, this is SPD if sigma times tau is smaller than 1, because the norm of this k is now just 1. And again, if we now iterate, un plus 1 is equal m plus a to the minus 1 m un. We can rewrite this as m plus a un plus 1 contains m un. So that's the same thing. That's the same thing as we do the same thing as before, more or less. Here we have then 1 over tau identity plus a. Here we have 0. Here we have minus 2 identity. Here we have 1 over sigma identity plus b to the minus 1 times xn plus 1 yn plus 1 contains 1 over tau xn minus yn. That's over there. And here we have minus xn plus 1 over sigma yn. Okay. So, and if we solve this again, we have a look at the first equation now, because we want to solve this for yn plus 1. It doesn't contain, for xn plus 1, it doesn't contain yn plus 1 anymore. We multiply by tau to get the identity over here, and we see the first inclusion is the same thing as xn plus 1 is equal to the resolvent of tau times a applied to xn minus tau times yn. And for the second we have a yn plus 1 is equal to the resolvent of sigma times b to the minus 1 of yn plus sigma times 2 xn plus 1 minus xn. It's very similar to what we've seen before. But now we have resolvent and no operator k is present. So we call this iteration here star because we want to need that. Okay, so now is this a problem that we have these resolvent of the inverse of b? So let's assume we know b, but don't have any idea how to calculate b to the minus 1, and then we don't have any idea how to calculate the resolvent of b to the minus 1. But there is a so-called Moreau identity. This helps here. So the proposition goes as follows. 27.3. This is the so-called Moreau decomposition of monotone operators. So if you have a monotone and sigma positive, then you have that the let's do it like this: the resolvent of sigma times a to the minus 1 of x is the same thing as x minus sigma times the resolvent of sigma to the minus 1a of sigma to the minus 1x. So this shows that to apply the resolvent of a to the minus 1, you only need to be able to apply the resolvent of a, because all the other operations here are very simple. You have to divide x by sigma, then apply the resolvent of a, multiply by sigma, and subtract from x. So that's all straightforward to do as soon as you know what to make of this operator here. Okay, that's the Moreau identity, and for some reason I'm also not able to memorize this. I always have to look it up. But the proof is it's just a simple series of calculations, but sometimes it's not that hard to rederive, but sometimes it takes me some time. So let's say, so we start by setting the left-hand side to y, saying y is equal to j of sigma a to the minus 1x, and decode this by bringing the resolvent or this operator to the left-hand side, which gives you then identity plus sigma a to the minus 1 y contains x. Okay, so let's work on this. So we want to reformulate the stuff here, and in the end have y as something again, and y should be equal to this thing over here. Okay, so first is we decode that here. X is contained in y plus sigma a to the minus 1 y, and this we write as, we bring everything which is not a to the minus 1 to the left. It's x minus y divided by the sigma. This should be contained in a to the minus 1 y. So why do we do that? Because now we can apply the inverse of a. Inverting monotone inclusions is totally straightforward. If this is an a to the minus 1 of that, then y is an a of this. Okay. So now, yeah, that's true. Okay, now we need something like the resolvent of sigma to the minus 1 times a. So to have that, we would like to have this multiplied by sigma to the minus 1, but also added the identity. Okay, let's try if we can get there, and yeah, we can. What we do is we want to have plus x minus 1 over here. That would be nice. So we just do it. So we bring this y to the other side by subtracting y and adding x. So what we do is plus x minus y. And we get x is contained in a of x minus y divided by sigma, and then we have plus x minus y. So from here to here is just adding x minus y on both sides. So of course we could as well then divide by sigma because it's positive. And then we have 1 over sigma a x plus y, x minus y, sorry, x minus y over sigma plus x minus y over sigma. And this is now nice because this here is identity plus sigma to the minus 1a of x minus y over sigma. Oops. That's just equal here because we have the same arguments here. This was actually the goal. Now we have a complicated argument in a, but we need even the resolvent here, so we need to add the right thing over there. That's the same thing once again. And now it's just the matter that the inverse of this is the resolvent of j, the resolvent of sigma to the minus 1a. So what we get is x minus y over sigma is equal to the resolvent of sigma to the minus 1a applied to x over sigma. And now just solve this for y, gives us our claim. So y is then, so we multiply by sigma, bring this over here, and y over there, it's just x minus sigma times the resolvent of sigma to the minus 1a, sigma to the minus 1x. And this is what we wanted to prove. Okay, that's the Moreau decomposition. It's actually, yeah, I don't know, I find it always a little bit tedious to do, but it's nothing difficult behind that. Of course, we have a very simple corollary, which you could also use on Tomboll-Pork, if we apply this for in the case of subgradients. So corollary 27.4, the Moreau decomposition for proximal maps. Is so if f is proper CVX LSC, sigma positive, then you have the prox of sigma of the oops, there's a typo. There's the subgradient sign, it's too much. We just need the prox of the conjugate, so sigma times the conjugate applied to some x is x minus sigma, the prox of sigma to the minus 1 of f of sigma to the minus 1 of x. Okay, so this is just replacing a by subgradient of f, and then seeing that these are just so a is the subgradient of f, and then a to the minus 1 is the subgradient of f, adjoined by subgradient inversion, and that's it. Okay, so now let's apply this Moreau decomposition to our iteration star, which is still up here. So we apply Moreau decomposition to this star iteration. So of course the first one stays the same, x n plus 1 equal to j tau a, x n minus tau y n. And the second now is y n plus 1 is equal to, and now it's getting a little long. because we need to subtract a bit, replace this resolvent here by this guy. So, but we can work it out. It's actually not hard. So what we get, oops, oh no, it's there. So this argument here plays the role of our x, so we get it's yn plus sigma times 2xn plus 1 minus xn minus sigma times the resolvent of sigma to the minus 1 of b applied to the same, this here divided by sigma, so it's 1 over sigma times yn plus 2xn plus 1 minus xn. So this is just the iteration expressed in the resolvent of a and b. And we've shown what is clear is converges, or this xn converges to a solution of 0 is in a plus b times x. If one exists and tau times sigma is smaller than 1 and positive. Okay, so that's nice. Okay, so but this is a little bit annoying here because of one fact. So this is now not kind of the most important thing. You could be happy with this. You could always choose sigma times tau, basically like 0.99 or something, and then everything is fine. But what I wanted to show is the case sigma equal tau equal 1 not covered, but it has a nice special structure. So let's write it down for the case of sigma equal tau equal 1. Then you get xn plus 1 is resolvent of a x minus xn minus yn, and yn plus 1 is equal to yn plus 2 times xn plus 1 minus xn minus resolvent of b of yn plus 2xn plus 1 minus xn. And what I want to show you here is now that for the iteration you can get rid of one of the variables. You don't need both of them. So here it's kind of inevitable. You need both variables to move forward. Here you only need one. And this can be seen by introducing or substituting wn as this xn minus yn. And replace then yn is then xn minus wn. So with this we get rid of y, so we replace y by w somehow. Oh, this takes a lot of space, these things. So if we do that, we get that xn plus 1 is equal to the resolvent of wn. Okay, this is just here. Now we, in this equation here, we replace all the y's by x minus w's. So here we get xn plus 1 minus wn plus 1 equal to xn minus wn plus 2xn plus 1 minus xn minus resolvent of b of xn minus wn plus 2xn plus 1 minus xn. So just replacing all the y's. So what we see here is that this guy cancels with that, this guy cancels with that, and here we still have xn plus 1 and 2xn plus 1, so we can cancel this one with the 2. Okay, so now the second inequality, the second equality here is we just multiply by minus 1 is wn plus 1 is equal to, and then both signs here flip. This is then wn. xn plus 1 is actually, so it's a plus, no, it's minus j of a of wn, and this turns into a plus resolvent of, and here we have let's call it 2 times xn plus 1. Xn plus 1 is ja of wn. 2 times this minus wn. So, and this is just one iteration which does not contain any x or y anymore. It's just one iteration in W. Okay, so we can just iteration in just one variable. But the catch is, if you iterate this, it's not really clear what the W does converge to. Actually, it's not really. I don't know, and it's not really clear. But we know that the x from before still converges to a solution, and the x, we still know that it's the resolvent of A applied to W. So what we can do is initialize with some arbitrary W0, iterate that guy here, and then this here, which you always calculate anyway, this is xn plus 1, and this converges to x star, a solution of 0 is in A plus B x. So that's also a nice thing. We don't know that yet. So why don't we know that? This would be nice if it would be like this, because then we would have the iteration just in one variable, and one of these variable intermediate values will still converge to a solution. But it's not clear, and the point is that our preconditioner was this one here. In the case sigma 2 equals tau equals 1, it's not definite. It's degenerate. So convergence is not clear, since our M in this case would be identity minus identity minus identity identity. And this is positive semi-definite. Actually, it has a kernel. So the kernel of M consists of the maps XX. Yes. Is the span of XX, of vectors of this type here. Okay, so but this, what I want to say, this thing here, these both guys together. Why is this of interest actually? Because it's a very old method. It's called Douglas-Redford method. And actually, Douglas and Redford invented this method back in the 50s, the 1950s, of course, to solve equations of the Laplace equation, actually. Or let's see, let's do like this, like equations like this, which they reformulated or spelled out. So in 2 dimensions, it's just this, and these derivatives here, if you discretize them, they lead to monotone or positive semi-definite matrices, so to monotone operators. And then to solve an equation like second derivative with respect to y is something that's simple even in 2 dimensions, because you can just solve a bunch of one-dimensional linear differential equations, and in discretized form they are just tridiagonal, and for tridiagonal matrices there's an O of n method. So, but for if you discretize the full Laplace operator, it's not going to be tridiagonal anymore, and the effort to solve this is quadratic in time at least. So, but then you can split up the solution of this full Laplace equation into a sequence of solutions of one-dimensional equations, which you can solve in O of n time. You can solve them very fast, and so they derived a method which is exactly like this. This is from 1956. And then later in, I don't realize, I think it's 1970 or 80, I forgot something. And so this was by, I forgot one of the names. Maybe I know, I forgot one of the names. So later it was recovered, I think it was in the late 70s or early 80s, by Lyons and some other guy, I forgot, unfortunately, that you can generalize what they done to monotone operators in general. This was already in the late 70s and early 80s. This method here what they just wanted to use to solve the heat equation, basically, or the Laplace equation, can be generalized to general monotone operators, and only in the early 2000s or 2010s, this method has been then broadly applied to split monotone inclusions and all the things which we've seen before. But it's still unclear. So they proved convergence by a spectral method. So because you know all properties of the matrices here, then you can investigate all the properties of the full iteration because it's a linear map. And if you control all the eigenvalues, then you're done. And this is what they did. Lyons-Mercier, yeah, this was Lyons-Mercier. So Lyons-Mercier, I guess it was 1970s, 80s. Did this for general linear monotone operators, and they also proved convergence kind of by hand. So of course not with the spectral methods, because eigenvalue is not a thing for nonlinear operators, but kind of by hand method using monotonicity and some clever places, and then that somehow like we also proved convergence for the proximal point methods like that. And now we have a challenge. We have this iteration here. We know it converges by these old results by Lyons-Mercier. But our theory just fails on the edge. This is just on the edge of what we can prove. And this is a little bit disappointing, I think. So it's, we can't prove it like this. We can prove it for a method like this if at least one can be 1. So you can, for example, set sigma to 1. But you can't set tau to 1 at the same time. It's not covered by our theory, and this is a little bit annoying. And the only reason is that you lose positive definiteness here. And what we do in our last lecture is some pretty new stuff. Student in my group, Emanuele Rinaldi, and co-worker in Graz, just proved that general theory for degenerate preconditioners, and we're going to cover that in the next lecture here. Okay, that's it for today. Thanks for listening. And see you once time again for the last lecture tomorrow.